I'm really sorry I couldn't be there. One of the unexpected things about having a toddler in daycare is that you can never expect to be healthy at any given time. But having said that, it's a great honor for me to be giving these talks. I really enjoyed the previous installment of this conference 10 years ago, and I encourage all my students to attend it. And I'm very happy to be here. So the goal of this series is to talk about p-adic Hodge theory and algebraic geometry. And what I want to try to convey is that it's a symbiotic relationship. There are applications of p-adic Hodge theory to questions in algebra and algebraic geometry, and I will talk about one of these applications today. But the flow of ideas also goes in the other direction, where we can sort of reinterpret objects in p-adic Hodge theory as really I'm trying to understand the geometry of certain algebraic varieties of really certain algebraic stacks. And then tools from algebraic geometry can help us. And so I'll try to convey both sides of this during these talks. But let's get started. So before I get into the meat of it, let me just try to frame the first half of this talk around a question in algebra. This question was the one that motivated me to get into p-adic Hodge theory in the first place, and it's pretty elementary. So it hinges on the following definition. So let's say R is a commutative ring. Then R is a splinter.
Sorry. I think it'll need you'll need to write larger just because of the setup.
Wait, sorry. How much larger? Is this better?
Yeah, people say yes.
Okay, I will try to write larger. Great. So right, R is a splinter. This is a definition. If it satisfies the following condition. Sorry, Joe Waldron tells me I should make my pen thicker. Thank you, Joe. Let me try. Okay, I'll take that as a yes to continue with this. Okay, so if it satisfies the following condition, so for all finite injective ring maps F, there exists a R linear splitting. So not a splitting in the world of algebras, but a splitting in the world of modules. And so why is this condition interesting, or what is it trying to capture? So let's first do the easiest example of this. So in characteristic 0, the situation is relatively tame. So let's say R is a Q algebra. In this case, it's easy to see that it's a splinter if and only if it's normal. And the reason roughly is that if you're in characteristic 0, you can look at the trace map, which goes in the other direction, and then divide it by the degree of the map, and that gives you a splitting, and it's a canonical splitting, so the argument kind of works in both directions. And the question that I was interested in 10 years ago, or 15 years ago in my thesis, was about trying to understand this property away from characteristic 0. It was motivated by the so-called direct summand conjecture, but I don't want to talk about that right now. Let me just tell you the theorem that was proven in 2010 and why that motivated what's about to follow. And so this was maybe 2010, and the theorem was the FP case of the splinter condition. So let's say R is a Noetherian FP algebra. Then the statement is that R is a splinter if and only if it satisfies the following derived version of the splinter condition. So you replace finite with proper, essentially, is the punchline. So let me write it. So for all F from X to spec R, which is proper and surjective, there exists, the map from R to R gamma of XOX splits in the derived category. So if you specialize to the case of finite maps, this is exactly, if you replace proper with finite, this is exactly the previous condition. But now we're sort of demanding more splittings. And so a priori, it's a more restrictive condition. And so what this theorem is saying is that actually in characteristic P, in the FP case, this kind of derived condition is no more restrictive than the underived condition. And one way to think about what the derived condition is saying is that it's some substitute for the notion of rational singularities, if you're familiar with those. So over the complex numbers, rational singularities satisfy this property over here of having these derived splinters. Derived splittings. And what the theorem is saying is somehow that the splinter condition in characteristic P feels more like rational singularities than like normality. And the question really I want to focus on is what happens in mixed characteristic. And so today's goal, or not all of today's goal, but a part of it at least, is to explain a mixed version and mixed characteristic. And so let me say, first of all, what I mean by mixed characteristic. I've already handled the case of, I've told you what happens for Q algebras, and I've told you what happens for FP algebras. So the only cases that remain are rings that don't contain a field. And this is what it means to be a mixed characteristic situation. And these are questions in algebra. And so they kind of formally reduce to the case where your rings are p-adically complete for some fixed prime p. You sort of do this, solve the problem separately, mod p for, or p-adically for every p, and then you can glue the solutions together because there's no funniness with these algebraic questions. And so the goal really is to explain a mixed characteristic version, or really a better statement is IE over SPUF ZP. And so this is going to be the base over which I'm going to be working through the rest of these talks. It's the p-adic completion of the integers. And so when I say work over SPUF ZP, that means that the rings that show up for me are always going to be p-adically complete for a fixed prime p that I maybe should have fixed at the start of time. So let me actually do that. Fix a prime p today and for the rest of time. Okay, so that's the question I will try to explain a solution to. Now let's put the question aside for a moment. Let me sort of do a detour, because the solution to this problem entailed developing a lot of technology in p-adic Hodge theory, and I want to tell you about some of the things that came up along the way. And the way I'm going to try and present the solution today is in this language of geometrization, which is a mechanism for turning kind of more questions from other fields into questions in algebraic geometry. And so let me explain the most classical instance of this. Oops. So let me explain geometrization over the complex numbers, or over any field of characteristic zero, actually. This is following the work of Carlos Simpson, and it motivated what happened later p-adically. So let me say K is C, although it could be any field of characteristic zero. And X over K is a variety. It could be smooth, doesn't have to be. And so the key definition is the following. Maybe I should attribute the definition to Simpson. Oops, sorry. I apologize. I don't know what happened here. Give me a sec, sorry. Know how this works. Let me just. Okay. Always restarting the thing works. Okay, sorry. So right, what was I saying? Right, this definition is due to Simpson. And it's going to be a device for turning questions about the Rham cohomology into questions about algebro-geometric objects. And so it's a functor that he attaches to X, which is called the de Rham stack of X. It's a functor from K algebras to sets. And it has a very simple definition. So X de Rham evaluated on some test object R is just X evaluated on R reduced. So nothing fancy. And this very simple definition captures some rather interesting features of de Rham cohomology. And so one has the following theorem. It's a theorem due to Simpson, although it's essentially a reformulation of some old results of Grothendieck on the infinitesimal site. So the first statement is that if you look at the coherent cohomology of this de Rham space, or de Rham stack, whenever you have a functor on K algebras, you can talk about its coherent cohomology. this turns out to be isomorphic to the de Rham cohomology of X itself. So you've turned de Rham cohomology, which has to do with nonlinear objects, into coherent cohomology, which is more linear looking. And there's a version of this statement with coefficients. So quasi-coherent sheaves on X de Rham are identified with modules with integrable connection on X over K. Oh, vector, yeah. And so, or equivalently D modules. And so what this is saying is that if you're interested in understanding things about D modules, that's tantamount to understanding things about quasi-coherent sheaves on this stack. And so if you understand something about the geometry of the stack, you'll be able to say something about D module theory. And this is, in some sense, not a very deep reformulation, but it's extremely useful. And let me just point out 2 ways it turns out to be useful in math. One is that it allows you to formulate structures that show up on de Rham cohomology in a more geometric fashion. So on de Rham cohomology, for example, you have the Hodge filtration, and that has a natural kind of geometric incarnation on the stack X de Rham. I think maybe according to the slides, some version of this showed up in Daniel Litt's talks. Another thing it's useful for is that this is a very formal procedure. It didn't really care what X was. X could have been any functor on K algebras, and you would be able to make sense of X de Rham. And so this construction allows you to make sense of de Rham cohomology of exotic objects, things like in schemes or in varieties or in stacks or whatever. And so these are the ways in which this geometrization machinery has been useful in algebraic geometry, or in representation theory mostly, actually. And what I want to explain is now that we have a p-adic analog of this, and these talks are going to be about that. So let me say now what we're actually going to do. So now let's talk about geometrization over SPUF-ZP. And so let me just, I don't want to formulate precise statements now. We'll sort of do this over the course of the talk and next talk. But let me just say what the meta theorem is here. So, or what the picture is of what we are trying to do. So let's say X is a p-adic formal scheme. And these are the sort of, as I said, these are the basic objects I want to work with. If you don't like this generality, you can just think of the formal spectrum of a p-complete ring, or the p-adic completion of your favorite scheme. Those are, in fact, the most interesting examples to me. And so for p-adic formal schemes, we're going to construct a diagram. There exists a diagram of stacks, which looks like so. So kind of the primordial object is something called the prismatization. This contains a divisor, which is called X Hodge state. This has a natural compactification. So it sits as an open dense inside something called the symptomification. And the prismatization carries some additional structure. So it carries a Frobenius automorphism or endomorphism. It's a lift of the Frobenius on X prism mod P. A practical consequence is that this lets you talk about the perfection. So the inverse limit perfection along the Frobenius of X prism, which is the perfect prismatization. And then you can just pull back this divisor, and you get a divisor here, which is called the perfectoidization. Okay, so this is kind of what the main players are, and I'm going to be spending these talks elaborating on what these objects are doing. But let me just say what they're trying to do. So there exists a diagram of stacks such that if you did quasi-coherent sheaves on any one of these guys, X question mark, it's some category of interest in p-adic Hodge theory. And so let me give you just one example of this, how this works. So example, let's say X is a smooth variety over FP. Then it turns out that the coherent cohomology of this Hodge state stack is the de Rham cohomology of X, analogous to Simpson's theorem. And so this is the analog of the de Rham stack for objects in characteristic P. And using this, you can reformulate statements about de Rham cohomology in terms of statements about the geometry of the stack. And sometimes you can actually learn more about de Rham cohomology this way. So tomorrow, in my talk tomorrow, I will tell you some theorems along these lines. The plan for the talk today is to concentrate on this part of the picture, on the top line, which is essentially coming from the theory of perfectoid spaces. And then tomorrow I will be talking about this part, the prismatization. So it's sort of a generalization of the perfectoid theory. This compactification will unfortunately not show up very much in my talk. It's a little complicated to define, and it's extremely useful, but we have to do the other work anyways before we talk about it. So I won't talk about it, although my impression is that maybe it will show up in Tony Fang's talk there on Friday. And then in my final talk, I will talk about some theorems you can prove up here using knowledge you have down here. So it's kind of trying to use information flow in this direction. And the specific theorem I have in mind is the p-adic Simpson correspondence. Okay, so that's the plan of the talk. And so what I want to do next is just tell you a little bit about this object and what properties it has. Okay, so scrolling off. Okay, so maybe let me first say in words what this object is, and then I'll start the next section. So essentially, xperf is going to be the best possible approximation to X you can build if you only know about the theory of perfectoid spaces, but not the theory of schemes. And so I will make that precise in a moment, but just keep that heuristic in mind. So section 3, let me remind you what perfectoids are. This is one of the great definitions in arithmetic geometry in the last, well, I guess 15 years. It's due to Scholze and his PhD thesis, and it's a relatively simple definition. So let me just actually give it to you. So a ring R is perfectoid. So it's a condition on a commutative ring if it satisfies two conditions. If it can be presented as follows. So if R is equal to W of S mod D, where you have the following two properties. So first, S is a perfect FP algebra. So a ring of characteristic P where Frobenius is an automorphism. For such rings, perfect rings, the Witt vector construction is very well behaved. It's sort of a canonical integral lift of that perfect FP algebra. And then the second condition is that this element D, really I should say the ideal generated by D. It's the ideal that matters, not the element. So any element in Witt vectors of a perfect ring can be written as follows. So you take the Teichmuller lift of an element of S, and then it's plus P times something, just because the Witt vectors mod P is S. And so the conditions you demand are the following. U is a unit, and S is A0-adically complete. So the second condition is a completeness condition and can more or less be ignored. The critical condition is this one, and it really cuts things down to size. And I think find rather amazing still. And so I want to give you some features or some examples first, and then some features of this definition. So maybe the examples to keep in mind are the following. So first, this is supposed to be the theory of perfectoids is supposed to be a generalization in mixed characteristic of the theory of perfect FP algebras, and it's the following justifies why this is true. So let's say R is an FP algebra, then it's perfectoid if and only if it's perfect. So for rings of characteristic P, this is nothing but the condition that Frobenius is an automorphism. And one direction is relatively easy. If you have a perfect ring of characteristic P, you can just write it as W of R mod P. And the element D equals P satisfies these two conditions because this quantity goes away and this quantity is 1. But then there are more interesting examples like mixed characteristic examples. And maybe the simplest one to give is the following. So you look at OCP. So CP is the completed algebraic closure of QP. It's an infinite degree extension of QP. It's the completion of an algebraic extension. The ring of integers there is a valuation ring of rank 1, but it's not a discrete valuation ring. But it's an example of a perfectoid ring. And then once you have one example, there's a recipe to generate more examples by just copying the kind of things you might do in characteristic P. So you might want to adjoin an element X, but then if you're in characteristic P and you're trying to produce a perfect ring, you also have forced to adjoin all P power roots of X. So you join all of those. And then if you stare at this definition for a few minutes, you'll see that R has to be p-adically complete. So I p-adically complete R. And that's an example of a perfectoid. And there's many more constructions, but maybe for this talk, I'll just recall these two. And so why is this class of rings an interesting class of rings to consider? Here are some properties it has. So first is that perfectoids are reduced. In fact, they're even semi-normal. And in some sense, they behave like they're smooth objects. And so it's not at all obvious in the definition that these should be true, but it's not so hard to prove. And so if you're trying to detect all the information about X that you can only detect using perfectoids, this tells you that, first of all, you're going to have to forget about nilpotents. Second property I wanted to recall was that the category of perfectoid rings has some nice properties. So let's say if R is perfectoid, if I fix a perfectoid ring I'm working over, then if I look at the category of all perfectoids over it, sorry, over R, not FP. This category has all limits and colimits. So you can form fiber products, co-fibered coproducts, etc. Word of warning is to understand how this is working, you should think about what happens in characteristic P, and that's a good guide. So limits are just computed at the level of underlying rings. So if you have a bunch of perfectoids and you take their limit, it will still be perfectoid. But for colimits, you have to throw in some additional P fruits. So like if you're doing this in characteristic P, you would have to perfectify the colimit in ordinary rings, and there's an analog of this operation for perfectoid rings, which I don't want to get into. But categorically, it has nice properties. And then the final property I wanted to recall was the following. So this is what leads to almost mathematics. So let's say R is some perfectoid ring. And R bar I define to be the following. So you take R, you reduce it mod P, and you perfectify it. So you join all P power roots, or equivalently in this case, it's actually the same as just passing to the reduction of R mod P. Then this is a quotient of R, and it satisfies the following idempotence property. So you can take R bar, and since it's an R algebra, there is a multiplication map from R bar to R bar, and this map is an isomorphism. And in fact, this is even true at the derived level. And so if you like, what this is saying is that if you look at the ideal, which is the kernel of the map from R to R bar, that ideal satisfies I equals I squared, and moreover, in some derived sense. And okay, so this sounds technical, but why is it useful? It's useful because it lets me define a coarsening of the category of R modules, which is easier to work with, which is the category of almost R modules. And so this allows you to define the following object, which will show up later. So I'm going to define a category. The notation is going to be d hat RA. And let me write down what the definition is first and then elaborate on it. So first, you look at all p-complete R modules, and then you mod out by R bar modules. So it's a Verdier quotient. And so, okay, a few words on this. So first of all, I said modules, but I worked with complexes. Oops. I worked with complexes everywhere. Why am I doing this? Well, it's useful, but also in this theory, you always want to work with p-complete objects. If you work with p-complete objects, then it's sometimes hard to have good properties if you demand that you stay in the abelian world, simply because the p-adic completion operation has some non-trivial derived functors. And so the object that behaves well is the derived category of p-complete R modules. And so that's what the numerator is. And then this property over here, this idempotence property, ensures that if you look at the ones which have an R bar structure, that's actually a full subcategory. And so you can mod out by it. And this is called the almost derived category of R. I'll just say almost R modules. You can forget about this for now, but this was an invention of Falting's, and he realized that you get a lot of really nice properties over perfectoid rings if you work systematically in this almost world. And we will use that later today. Okay, so I think this is about all I wanted to recall about what perfectoid rings are. There's a ton more you can say about this. You can give an entire course on this. I have. But I want to get to where I promised I was getting to. So let's go to and try and talk about this perfectoidization. If there's any questions, please ask me. Otherwise, I'll keep going. Okay, so the geometric setup is the following. Just for technical purposes, I want to write down the world I'm living in. So I'm going to be consistently working with the category of p-nilpotent rings. And sheaves on those. So with the flat topology. So a p-nilpotent ring is a ring where some power p is 0. Any p-adically complete ring is the inverse limit of p-nilpotent rings. So if you understand what the functors you're trying to describe look like on p-nilpotent rings, you automatically know what they look like on p-complete rings. And we're going to work with sheaves on this category just to have more flexibility in our constructions. Okay, and so here's kind of a definition I want to give of the perfectoidization. So let's say X is some p-adic formal scheme. If you like, just take it to be spuff R for your favorite p-adically complete ring R. I'm going to define something called X perfed. And what is it? Well, it's going to be a sheaf in this category I just wrote down above, and it's the best possible approximation to X you can build using the theory of perfectoid spaces or perfectoid rings. And so there's a very stupid way to do this, and that's what I'm going to do. So I'm going to take just the colimit of all perfectoid rings mapping to X. So spuff maps from spuff R to X, where R is perfectoid of spuff R. Okay, so this is a horrible definition if I don't tell you more about it, but at least it captures this idea that all XPerf knows about is the information of perfectoid rings mapping to X. And this thing comes equipped with a natural map to X, just because every object on the left-hand side, each of these spuff R's tautologically comes with a map to X, and so therefore XPerf also has a map to X. Tomorrow I'll give a definition of the prismatization, which will really give you a functor of points description of this object, and that's the better thing to work with. But for now, let's just go with this. And so, what are some properties this object has that make it useful? So maybe the first property is that it's actually, even though this is some ginormous colimit which a priori you have no control over, it's actually much tamer than that. It's essentially an algebraic space in perfectoids, if you like. So you can write X perfed as U mod R, where R to U is a flat equivalential of perfectoids. So it's really not that exotic of an object. If you allow this, okay, I think someone's mic is on. If you allow yourself to work with perfectoids and modulo flat equivalentials, then these objects are in your worldview. The other property I wanted to mention is that the derived category of X perfed, it sort of behaves as you would expect based on this formula. So this formula is saying that X perfed is a colimit of things mapping in. So you would expect that invariance of X perfed would be given by the inverse limit of the corresponding invariance for spuff R, and that is indeed true, although it's not tautological from this definition. So this is the inverse limit over all spuff R to X of d hat of R. So to give an object in the derived category of X perfed is the same as specifying complex over R for every perfectoid mapping to R, and things have to be p-complete. All right, so that's the definition. What is the definition trying to do? So let me give you some examples of this definition. So the first example is that if R is perfectoid, then the definition does nothing. And this is easy to see. just because the colimit has a final object. Second is that if R is an FP algebra, if R is over FP, then this perfectoidization is something you might have encountered before if you studied characteristic P algebraic geometry, which is the inverse limit along the Frobenius of SPF R. Sorry, let me write this on a new line. So it's the inverse limit perfection of R, of spec R as a scheme, or equivalently the direct limit perfection of spec R as a ring. So in characteristic P, this notion of perfectoidization captures what perfections are, and in mixed characteristic, at least for perfectoids, it's not doing anything. I wanted to give one interesting example of this construction. So let me try to do this here. So let's say R is OCP, the perfectoid ring I mentioned before. So the ring of integers of the algebraic closure, p-adic completed algebraic closure of QP, and X is GM, the multiplicative group over SPF R. And so in this case, X perf has a nice description, at least in this almost world. So it's almost isomorphic to the following construction. So you take GM and you form its inverse limit perfection along the naive Frobenius, which I will write down in a second, and you mod out by a profinite group. So GM perf, notice the lack of a D. I'm sorry for the notation, but I think both of these things are standard. So there's kind of a P power map on GM, which plays the role of Frobenius integrally. And you just form the inverse limit perfection along those maps. And ZP of 1 is the profinite group of P power roots of profinite group given by the inverse limit of the compatible systems of P power roots of unity in CP. So it's abstractly, it's isomorphic to cyclic profinite group with p-adic profinite group with one generator. You think of a profinite group as a scheme by saying that each finite quotient of it is a finite scheme, and then you can take an inverse limit. And then GM perf has this quotient description in this almost world. And so this is just to indicate that the theory is non-completely stupid. It's doing something interesting in this example. And so let me now tell you some theorems one can prove using this construction, which maybe actually give a better feel for what this object is doing, why we care about it. So I want to talk about a Riemann Hilbert functor, just the very easy version of it for now. And then I'll talk about a slightly more complicated version in a few minutes. And so let me just straight away state, oh yeah, maybe I should say this is all joined with Lurie. All unattributed results today are joined with Jacob Lurie, including the constructions that came before. And so here's the theorem. I'll call this theorem A. So let's say X is a scheme. I will restrict my attention to scheme because the statements are easier to formulate here. I'm going to define the perfectoidization of X by just copying the previous definition for the p-adic completion. So I take the p-adic completion of X, and then I apply the definition I just told you about. And then what the theorem is saying is that you can understand modules over the perfectoidization in terms of étale sheaf theory on X. And so here's one way to say it. So there exists a co-limit preserving tensor functor which goes from the derived category of étale sheaves on X with p-adic coefficients, I'll call this RH, to this category, this derived category of X perf. Quasi-coherent sheaves on X perf. So it's a mechanism for relating étale sheaves to quasi-coherent sheaves, and therefore it should suggest to you it has some Hodge theoretic flavor. And I'm just going to tell you one property for now, which is that it commutes with proper push forwards. Commuting with proper push forward. And so actually, even though what I've written is very little information, it's in fact enough information to pin down the functor. You know where the constant sheaf should go. You know where finite push forwards of the constant sheaf should go. And if you have some familiarity with étale cohomology and how it's set up, that's more or less enough information to determine where any sheaf should go. The existence is not obvious, but anyways, this is the theorem. And so why is this theorem useful, or what can you do with it? So let me tell you one corollary you can prove which answers this question, which I started off the talk with. So the corollary is the following. So let's say f from x to spec r is a proper map of Noetherian schemes. Not necessarily in Kiersik P anymore. I want to go back to the splinter equals derived splinter condition. And then what the theorem lets you do is it lets you prove that, there exists a finite cover pi from y to x, such that if you look at the pullback on cohomology in positive degrees, this map is zero, is divisible by p. So it's a very the relatively simple statement in algebraic geometry. You can formulate it as soon as you know what proper maps and cohomology are. In Kiersik P, this was the essential input in proving the splinter equals derived splinter property I mentioned before. And similarly over here, this implies that splinters are the same as derived splinters over ZP. So for p-adically complete Noetherian rings. And so it answers this question I had before, and just heuristically, the idea is that the difference between the two conditions was proper maps versus finite maps. And at the level of cohomology, the difference between proper maps and finite maps comes from higher cohomology. And what the corollary is saying is that the higher cohomology kind of goes to zero after going up along finite covers. So cohomologically, you can pretend that they are proper maps. You can turn that into a rigorous proof. And so what does this theorem have to do with, what does the corollary have to do with the theorem? Because they don't a priori look like they have much to say with each other. I don't want to give you a full proof here because I want to tell you some more theorems, but let me just tell you what the idea is because it's very easy. So you use the Riemann Hilbert theorem above to reduce to to turn this question in coherent cohomology to a question in étale cohomology. And you reduce to more precisely the following lemma, which is elementary, but was really fun for me. So if X is a normal scheme and the field of function is algebraically closed, so such schemes are really big, and the X's you're going to apply this theorem to are going to be things you get by taking inverse limits of all finite covers. You can repackage this vanishing assertion here as a statement about the cohomology of that inverse limit. And that's the object to which you apply the theorem. And then the lemma says the following, that in this case, the constant sheaf ZP is extended from the generic point. So it's the lower star extension of the constant sheaf from Kx. And so kind of all the full étale sheaf theory on X kind of collapses to what happens over a geometric point, which is its generic point in this case. And that makes étale cohomology go away, and then via the Riemann Hilbert theorem, that essentially lets you make coherent cohomology go away. So that's the rough idea of the proof. As I said, it's not a full proof, but it hopefully gives you some idea of why such a theorem might be useful. Ordinarily, if I was giving this talk, I would have been pausing to take a lot of questions, but I think it's not exactly compatible with the setup of the talk. So let me keep going, and I'm very happy to answer questions afterwards. Okay, this is section 5. Okay, so let me tell you some more refined properties of this Riemann Hilbert construction. Some finiteness. So far I've just told you that there's a functor from étale sheaves to coherent sheaves, and it has some nice properties. And the formal properties were enough to get some coherent cohomological vanishing consequences. But really, if you want some theory that should be called Riemann Hilbert, it should respect finiteness conditions. And the finiteness condition should moreover be things you can work with. And so that's what this theorem is going to be about. And so now the setup is going to be more specialized, because if you want finiteness conditions on the sheaves, you better impose some finiteness conditions on your spaces too. And so let me work with C over QP, which is a perfectoid field. You can take it to just be CP, the p-adic completion of the algebraic closure of QP. And then X is my geometric object, is going to be a finite type scheme over it. And so theorem B is the statement that this perfectoidization construction actually has very good finiteness properties. So X perfed, mapping via pi to X. Let me first say it heuristically. So it behaves like a finite map in the almost category. And so what do I mean by this? I mean it has roughly the same finiteness properties you would expect X to have. So two specific statements you can say is that there is a good category of coherent sheaves in this setting, which is almost coherent sheaves. And almost coherence is, let me write this down, almost coherent sheaves. And this property of being almost coherent is both preserved and detected by push forward along pi. So this is the sense in which it behaves like a finite map. The finite morphisms have the property that coherence can be preserved and detected along by push forward along finite maps. And secondly, there is a notion of Grothendieck duality on X perfed, and pi lower star intertwines Grothendieck duality. So these almost coherent sheaves come equipped with an internal notion of Grothendieck duality, and it's compatible with pi lower star. So roughly, at the expense of living in this world of almost mathematics, you can pretend that X perfed is a finite scheme over X. Not too much is lost. And so what this is saying is that there is a good finiteness condition on the coherent side, which is almost coherence. And if you recall, in the Riemann Hilbert functor that I mentioned before, the target was quasi-coherent sheaves on X perfed. So on this side, I just told you that there is a reasonable finiteness condition. On this side, there's a very classical finiteness condition, which is constructibility, which is important for Grothendieck and all the subsequent work on étale cohomology. And so part C of this theorem is, let me first say something more before I say what happens under the finiteness conditions. So I have this functor RH, which is going from ZP sheaves on X étale to quasi-coherent sheaves on X perfed. Now, on the ZP sheaf side, I have a subcategory consisting of sheaves supported on the special fiber. On the X perf side, I have the subcategory consisting of the things that were almost zero. So that was, again, sheaves supported on the special fiber. And since the functor is compatible with proper push forwards, I get a functor on induced categories like this. And so on the left-hand side, this is just another name for sheaves on the generic fiber. X eta stands for the generic fiber. And the right-hand side, I had I had told you that this was by definition the almost category of X. Perfect. And so what I've just convinced you now is that there's actually a functor from sheaves on the generic fiber of X to almost quasi-coherent sheaves on X buffed. And so this is now a mechanism to relay just information happening on the generic fiber, topological information on the generic fiber to coherent information on your integral object. And so theorem C is the statement that this functor is compatible with duality and has other nice properties. So this almost version of RH takes constructible sheaves to almost coherent sheaves. So it preserves your finiteness condition. And commutes with duality. So on the constructible side, there is something called Verdier duality, which is classical duality for sheaves on a manifold generalized to this context. On the right-hand side, I have this notion of duality that I just told you about, Grothendieck duality. And this functor is compatible with those notions. And it has good T exactness properties for certain T structures. And so, okay, these are abstract statements, but let me just tell you the concrete consequence it has, which is really how it ends up being used. So if you take this almost Riemann Hilbert functor applied to a perverse sheaf on the generic fiber, then what this theorem is telling you is that its output is a perverse sheaf on X puffed, which, as I just told you, so X puffed you should think of as something finite over X. And so if you want to understand sort of qualitative properties of sheaves here, you might as well just push them forward. So let me tell you something about the push forward of Riemann Hilbert partner of a perverse sheaf. And the statement that you get out of what's written above is that this is a Cohen-Macaulay complex. So sorry, let me just write CM for now. It's a CM complex. So if you remember from commutative algebra, Cohen-Macaulay modules are certain modules with lots of good local vanishing properties. Their local cohomology at various points vanishes basically until you hit the dimension. So from the point of view of coherent cohomology, it kind of feels like it's smooth at that point. And what this theorem is saying is that there's a big supply of such modules coming by applying Riemann Hilbert to perverse sheaves on the generic fiber. And this is the form in which this theorem has been most useful. And so I just want to end my talk by spending about maybe 5 or 6 minutes on some applications of this theorem. And maybe those applications are more convincing than the theorem itself. So the first application I wanted to mention was this theorem lets you prove a version of the Kodaira vanishing theorem in mixed characteristic. So the Kodaira vanishing theorem is not true in positive or mixed characteristic. On the nose, the literal statement fails. But what this lets you do is that it lets you prove a version of Kodaira vanishing in mixed characteristic up to finite covers. So whenever you encounter some instance of Kodaira vanishing that's not true in mixed characteristic, what the theorem will, or this application is saying is that there is some finite cover of X where that sort of bad cohomology class disappears. And this has a lot of applications in birational geometry and the minimal model program. I don't want to talk about them here because there was an entire lecture series in week 1 about these applications. So I'll just refer you to the lecture series, and the notes are all on the SRI website. What I wanted to mention, however, was a new and somewhat surprising application of this that was just recently observed by Louis Pan. It's not like a major theorem yet. It's more like a lemma, but I found it quite striking because it's a property of a certain morphism which I didn't expect to have any good properties. So Louis Pan showed. So using this property over here, essentially, Louis Pan showed the following. So this is maybe more for experts, but let me at least write it. So the Hodge state period map pi Hodge state. It goes from you take AG, minimally compactified, with full level structure at P. And Scholze constructed a morphism from this object to the Lagrangian Grassmannian for the symplectic group. And this period map is extremely useful in applications of perfectoid machinery in the Langlands program. And the conventional wisdom was that somehow this map, although one can define it as the level of adic spaces, it's a very badly behaved map. And indeed, it's true that the fibers over some points look like they're disks, and over some other points, they look like they're profinite sets. So it doesn't feel like it behaves nicely at all. But what Louis showed is that actually it's almost flat at the integral level. And so it does actually have good properties that you would expect a family, flat family to have. It's just that because of the infinite dimensionality of the situation, some of your intuition is maybe a bit off. And so my feeling is that this is actually the start of something. There was one other result of Louis and Kai Wen that I wanted to mention, but I will not do it for the lack of time. And let me actually just end my talk here. I'm happy to answer any questions.
Okay, thank you very much. Are there questions? So wait for the microphone to be done.
Hello, thanks for the break. So, I was curious about the description of the perpetualization of GM that you mentioned. It seems that CP of 1 is a subgroup of the 90 limit that you wrote. So is the quotient just a usual quotient, or what is quotient?
Sorry, so let me. The question was, in what category is this a quotient? Or
Yes, it is.
I mean, the quotient is just a quotient in this category of sheaves on p-nilpotent rings with the flat topology. The point is that this is not, sorry, ZP of 1 is not a subgroup of GM perf. If you thought of it as a group scheme, it would be a subgroup of this group scheme. But I'm only talking about its points and regarding those points as a profinite group. So somehow on the generic fiber, it's a subgroup, but on the special fiber, it's entirely been collapsed.
So the bar in RCT1 is that you're not looking at the subgroup scheme, or?
No, the bar means it's the constant sheaf on this profinite group ZP of 1.
Okay, thanks.
Mm-hmm.
Can you say a little bit more about the Hilbert flatness of this map? This seems pretty remarkable. That's not because it's not dimensional.
Yeah. So I think the question was about the almost flatness of this map, right?
Yes.
So I can only convey my understanding of it. So my understanding is the way Louis proves this is by a version of the miracle flatness lemma. Essentially, you first show that the constant sheaf, so this is some perfectoid space, and you show that the constant sheaf on this perfectoid space is perverse. And then this some limit version of this statement lets you prove that it's Cohen-Macaulay. And then the local rings over here are regular. And then Peter Scholze had constructed a sort of factorization of this map, mod P, which looks like it's an integral map followed by a finite map. And so using that combination plus the miracle flatness theorem gives you the almost flatness. That's roughly the idea.
So with your stated properties of this perfect conjugation, do you need any assumptions on the forms?
For which properties? For the first, no, this is completely general. And it's important that it's completely general because eventually I want to apply it to like big objects like this.
Sorry, I mean the properties of a perfect conjugation.
Sorry. Here.
Yes.
I don't think you need any assumptions for what I've written on the board.
I had a question about theorem A. I was
not sure if there was some additional condition. It looked like maybe the zero functor satisfied that. Yeah.
Oh, so tensor functor for me means symmetric monadal functor. So it takes the unit object to the unit object. So ZP would go to the structure sheaf here.
Okay.
Good question.
Any more questions?
Maybe I can ask one on Zoom if it's okay. When you were saying this Riemann Hilbert functor was perverse T exact, what was the perverse T structure on that target category, the coherent category?
Yeah, so that's a bit tricky to define. The simplest description I can give The simplest description I can give of the perverse T structure here is first on perverse coherent sheaves on a scheme, there is a perverse T structure. Sorry, on coherent sheaves on a scheme, there's a perverse T structure that was studied by Deweyne, Bezrikov-Nikov, Orinkin, etc. It's somehow the Grothendieck dual of the standard T structure. And so the way you define it for xperft is basically by trying to sort of just turn this meta theorem into a theorem. So something is perverse co-connective on xperft if and only if its push forward to x is perverse co-connective. And then the connective part is formally the left orthogonal to that, and there's some description you can give. It's not super satisfying, I think. But the co-connective part is something that you really can get your hands on, and that's what's relevant for this Cohen-Macaulay property.
Is that definition using something about the geometry of this xperft, or it's totally general?
It's using a tiny bit. It's using the fact that X is a finite type scheme. So the finite type assumption on X over OC allows you to write down a good perverse T structure on X. And it's using I'm essentially saying that I'm declaring the perverse T structure to be the unique T structure such that pi lower star is left exact. And so your question is basically, what am I using? If you're asking what am I using beyond the fact that X is finite type, I guess the proof uses certain properties of xperft. So I said that xperft has these atlases, U mod R, and the precise atlases we need to run this argument are those of the form U mod R, where U to X is a universal homeomorphism mod P. So that's just the technical input that's needed.
Thanks.
Mm-hmm.
So over characteristic zero, when you have the Riemann Hilbert functor, if you have some, if you restrict to like an appropriate subcategory, you get some equivalence. Is there some kind of analog that you get for this? Yeah, Riemann Hilbert functor.
Sorry, I didn't follow the first part of that. Could you just say it a little slowly because the connection is not that great?
In characteristic zero, if you restrict to some appropriate subcategories, then the Riemann Hilbert functor comes in equivalence. Is there some analog you get in this world?
So right, that's a good question. I do not know an answer. So maybe one thing I should have said is, so I was trying to simplify the discussion. This functor was going from étale sheaves on X on the left to quasi-coherent sheaves on xperft, but really it has a refinement. And the refinement goes to this sort of prismatic version of xperft, which is some one parameter thickening of xperft. And when you think of the functor as taking values there, it takes values in Frobenius modules there. And so if you keep track of the fact that it's taking values in Frobenius modules on this prismatic thickening of xperft, then the functor is fully faithful. And then it's reasonable to ask, what is its essential image? I have tried to think about this question, and there are some natural guesses you can make. Like if you restrict to constructible sheaves on the left, then it should be exactly those Frobenius modules which are almost coherent, mod D, but I don't know how to prove it. So if X was equal characteristic P, there is such an answer, and I would be very interested in knowing if there is an answer like that in mixed characteristic.
Okay, looks like there are no more questions, so thank you very much again.